So on the backboard, you see this is where we're headed. Actually, we've already been discussing a lot of this. It's just now we're going to do it analytically. We're going to answer all of those questions about a function, and we're going to actually be able to sketch a function, and then we're going to test to see if it matches by using calculus. So I'm going to give us a function, and then we're going to see if we can figure out what it looks like using calculus. So let's do an example. X cubed minus 6 plus 15. What? That looks kind of suspicious. Okay, so let's do an example. Given f of x is equal to x cubed minus 6x plus 15. Okay? Anybody know what that looks like exactly right off the top of your head? Aside from a couple of people here. Now that's kind of hard to tell. We know it should go like this in some way. Okay, it's cubic. But aside from that, we don't know much. What we're going to do right now is we're going to find critical numbers where the function is increasing or decreasing, and where it has relative or global maximums and minimums. And then we're going to actually sketch this thing, and we're going to see how close we came. So we're going to do it all. Well, there's actually one more thing that we have to do, but that's something else. We have to learn their concavity. So let's go ahead and do it. So step one. So step one, we're going to find the critical numbers. And so to find the critical numbers, we find the derivative and then find where it's either equal to 0 or where it's undefined. So f prime of x is equal to 3x squared minus 6. So this is a polynomial function, which means it's never undefined. So we're not going to get any critical numbers from being undefined. But if we set it equal to 0, then we should be able to get some answers here. So let's solve this. We get this is 3x squared is equal to 6, or x squared is equal to 2, or x is equal to plus or minus the square root of 2. So step one, there are two critical numbers, and they are at positive square root of 2 and negative square root of 2. All right, step two. Step two, we're going to make a chart. Okay. Make the chart. Okay. So let me show you what the chart means. All of the times prior to this, like all last week, we were able to tell where the function was increasing and decreasing by looking at the graph of the derivative. Remember we said wherever it's above 0, it's increasing, below 0, it's decreasing. We don't have that luxury here. Okay? What we're going to do is we're going to do it analytically. That's what this is all about today. So we don't have a graph of the derivative. We're going to use it analytically. So watch this chart. So the chart is a t-table that goes sideways. Okay? It's a sideways t-table. and where these are going to be x values here, and these are going to be values of the derivative here. Okay? And there's a reason why it's sideways, and hopefully you'll be able to gather that. Now, think about it. We want to find out where the function is increasing or decreasing. Okay, so we just need to know, hey, where is the derivative positive and where is the derivative negative? Well, I'm going to pick two values that I know for sure what they are. The square root of 2, the negative square root of 2 and the positive square root of 2 are two x values. What is the value of the derivative at negative square root of 2? 0. We just figured that out right there. These are where the critical numbers are. Okay? So we can put a 0 in the t-table for f prime for both of those. Now stop and think about it. Remember when I said that critical numbers are like the magic places? If something's going to happen, if there's going to be a maximum or a minimum, the only place that it can happen is at a critical number. It can't happen anywhere else. Therefore, what we're going to do is we're going to test numbers numerically to the left and to the right here, and we're going to find out what the value of the derivative is, and we're going to know that this is where the function is increasing or decreasing. Okay? So, we need a value. What's a value between negative square root of 2 and positive square root of 2? 0. So that's a good one to pick. Okay. What's a number to the right of the square root of 2? 2, because that's about 1.4, so 2 is a good number to put here. And then a number to the left of negative square root of 2 would be negative 2. We're making a t-table, and it's actually representing a number line that's going to be able to help us determine what's going on here. Okay, so now watch this. Now we're going to take these values here, and we're going to plug them into the derivative. See what it did there? So, we're going to plug in the numbers. So let's do the easiest one first. So you plug in a 0 into the derivative, and you get negative 6. Now the only thing that matters here is the negative sign. That means between negative square root of 2 and positive square root of 2, the derivative is always negative. For every single value in between. It didn't even matter which number that we picked. 0 was really easy, but it would have taken anything. And it always would have been negative. All right, let's plug in a negative 2 in for x. And what do we get? You get 12 minus 6, so it's a positive 6. Guess what? The derivative is positive to the left of negative square root of 2, which means the function is increasing to the left of negative square root of 2. Last one, 2, plug it in, you get 6, and it's positive. So guess what? This little chart is pretty handy, because this is what it tells us now. It tells us that f is increasing here. So f is increasing here. F is decreasing here in that interval in the middle. And that f is increasing here. Better yet, if the function is increasing, then decreasing, what's happening right here? There's a maximum. So this is where a max occurs. And then if the function is decreasing, then increasing, this is where a minimum occurs. Now, the chart all by itself is, they have a thing for it on the AP exam. They say it is not proper justification. That means if you leave the chart and you say, well, duh, look at it. It's decreasing. Just look at the chart. You get no points, 0. So you have to do this step right here, which is step 3. This is the justify. We should state and justify. So let's do them right from the top. Let's do increasing first. So we say f of x is increasing on, now we got to state the intervals. What's really amazing is you could have tested any number to the left of negative square root of 2 and this still would have been positive because the function is increasing on that entire interval. So we're going to say from negative infinity up to and including negative square root of 2. See the bracket? The bracket was the ladder example. You got to be able to take that last step. So it's increasing on this one, comma, and then it also is increasing from the square root of 2 up to positive infinity. And then we have to state why. This is big. Because f prime is greater than 0. Then we do exactly the same for decreasing. F of x is decreasing on the interval from bracket negative square root of 2 to positive square root of 2 bracket because f prime is less than 0. What we're doing now is we were doing it visually all last week. Now we're stepping away from the visual and we're doing it analytically. Okay, so we got this one, this one. Now we state max or mins. So we say that f of x has a maximum at x equals negative square root of 2. And the reason that you'll always put is because f prime changed, we'll say changes from positive to negative. That's the justification as to how we know there's a maximum there. And finally, f of x has a minimum at x equals a positive square root of 2 because f prime changes from negative to positive. Any questions there? Let's see how we did. So, pull out your graphing calculator. Excuse me. I'm going to try to make this big. Tell Amy we didn't miss her. No, that's not nice. Okay. Now I'm having you use your calculator because you're going to have to know how to use the features on here. So, yeah, this is crooked. Okay. So, punch your original function in. And let's validate. Let's see if this matches with what we said. Oh yeah. How come it didn't? How come it went back there? It just must. It likes you. Maybe you have. You've got magnetism. Okay, let's see if this actually works. I don't know how clear that's going to come out. All right, graph your function. F of x is equal to, so y equals x raised to the third minus 6x plus 15. That's a good question. I don't know. I can't because it's got to have this. Yeah, this is a teacher's yeah. Okay, so we're going to see if this thing matches, if our prediction matched what it's supposed to. So I'm going to do a zoom 6 as a standard graph, and that looks pretty good. Okay, so we can't tell a thing from that, so let's change our window a little bit. So now how you go about this is your own business as long as you know how to do it. We want to get a decent window here. So I'm going to just try quickly a zoom out and see if that gets us anywhere. Okay, that does give me something there, and I can see where the wiggle is. I'm going to do a zoom in now, but I'm going to do a zoom in right in the middle of this thing. Put my crosshairs right there, and then enter. So it looks like that. Now I'm going to widen this a little bit so we can see it a little bit better. So I'm going to change my window. Right now my window is negative 10 to 10. I'm going to go negative 5 to 5. Okay. The whole purpose in this is just so that we can get a better understanding and make sure that we're matching what we thought we were supposed to. Okay? Everybody got a good window now? Yes, ma'am. Zoom fit, if it works, the old algorithm I know was horrible. Zoom fit just never worked. Did anybody try Zoom fit? And did it work? Good. You have a new operating system? Can't remember. You were one. Hey, if you can do a Zoom fit and it gets you something like this, awesome. But I've known it to be very unreliable. All right, so where is this going? So I want to identify the fact that the function, everybody agree the function is going, it's increasing here to here, and it's increasing from here to here. Okay? Let's find where those values are. So we can go find a maximum. So this is one of the things you need to know how to do. So second calc, find your maximum. And then you got to give it the left bound and right bound. So left bound and a right bound. And then some guess in between. 1.414212. That's 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 a negative square root of 2. Okay? If you don't believe me, watch. Second quit, what's the value of x? Remember, it remembers the last thing that you did. I found a maximum, and it knows what x value it is. And then if I do the square root of 2, bada bing, bada boom. Except it's a calculator error because it actually computed the maximum as opposed to calculating the maximum. Okay, back to the graph. Go find your minimum. Let's see if that matches up. Second calc minimum. So, again, I got 1.41 here. That's the square root of 2. That matches our chart, and it matches our justification. Right on the money. Does that make sense? Okay, so this is proving. This is proving that how we did it analytically actually works. But now let me show you something really cool. All right, go back to a Zoom standard. Okay, now I'm not going to move my screen, but I am going to identify this as a negative square root of 2 and this as a positive square root of 2. Okay. See what I did there? I just brought this down. This is where the x was. That's where the maximum and the minimum occurred. Oh, wait. All right, we'll put it back. We'll put it back once we graph it. What we're going to do now is we're going to graph the derivative. I'm going to show that what you learned last week from a visual standpoint matches up with what we've got here. So go to your y equals. And now we're going to graph the derivative. So you gotta use the math button on the left. Math on the left. And it's hiding, it's below the surface there. So you got to go down to number 8. And you get numerical derivative. Now, if you have the new operating system, it looks like this. If you have something that doesn't look like that, let me know, and I'll help you out. So what do? We're going to find the derivative with respect to x. So you put an x right there. We're going to find the derivative of y1 here. So I want y1. So that's under vars, and it's your y vars, and it's your function y1. See, so we're graphing the derivative of y1, and then we're going to graph all x values. So we're going to put an x here. Everybody see what that looks like? Now, if you don't have this one, real quick, then you do this. And derive y1 x comma x. That's what you do if you don't have the updated system. Now we have to change our window on our x's. This has to go back to -5 to 5. Thank you to Lindsay for catching that one. And we'll graph it. Oops. Oh, that's the first one. Here's the derivative. Okay. Actually, I'm going to redraw it, but I'm not going to graph the first one. So you guys know how to do this? If you select on here and press enter, then it doesn't graph it, right? You just have to go on the equal sign. So I'm only graphing the derivative now. This is the 3x squared minus 6. You see what's going on here? This is the graph of the derivative. It's exactly what we did in the chart, because look at, this is where the derivative is all positive. This is where the derivative is all negative, and this is where the derivative is all positive. Okay? And this is our maximum point. This is where the maximum occurs, and that's where the minimum occurs, because the derivative changes from positive to negative, minimum, negative to positive. Does this make sense? This matches exactly what we did all last week, but now we can do it analytically without the graph of the derivative. But you can test it now. Yeah. All right. The new assignment is page 186.